All right, finishing things up. We left off right here with the generalized inverse stuff. Let's make one final observation here. From part 3 and 4, this thing we just proved, leading us to these vectors z. For any z, we have a solution of this form, and for a solution, there is a z, for which that solution can be written in this form. What we get by combining those two is we see that the number of linearly independent solutions of ax equals b for given b is the rank of this matrix here, I minus generalized inverse times matrix A. That's what we're getting as we vary the z's is different linear combinations of the column of this matrix. This matrix in parentheses, where it has components, the coefficient, that linear combination that you. So rank matrix, like this, the solutions. The rank of that matrix by an earlier result we saw was m minus the rank of A. Okay, so we're going to tie this in with a different space, the space you've dealt with before, the null space of a matrix A. Recall, for in matrix A, excuse me, the set of all vectors generated by solutions of the homogeneous system of equations, ax equals 0, is called a null space. If you view A as representing a linear operator, the null space is the stuff mapped to 0 by that linear transformation. It'd be called a kernel, maybe in a more algebraic setting. But it's the space of all vectors that are mapped to 0 by multiplying them all left by matrix A. The dimension of null space is nullity of A. So stuff from linear algebra. You sure this null space really is a vector space? We'd have to do is show closure under linear combinations, and that would be a total piece of cake. You apply matrix A to a linear combination, you get a linear combination of A applied to 2's. And when you apply A to elements of the null space, you get 0 vectors out. Is a vector space. A claim about the null space, something we'll come to at some point. The nullity of n by m matrix A satisfies the dimension of A equals m minus the rank of A. And remember, m is the number of columns of A. We could rewire this. We'll go through proof of that shortly. We could rearrange this equation to read the rank of A equals m, the number of columns of A. You're used to this from linear algebra, where when you take matrix A and reduce it, the pivot containing columns contribute to the rank. The pivot free columns contribute to free variables, if we treat it as a system of equations, and ultimately to the null. Goes together and you get all of the columns of matrix A. Okay, let's go through proof of 3.5.4. Okay. If we take an element of the null space, by definition, that element x satisfies x equals 0. And we know that we can write solutions in a certain form. We were writing solutions in the form, let's take theorem 5.3. See specifically where we're aiming. Theorem 5.3 is this form. We're writing solutions by the generalized inverse, we'll set a zero vector here. So we'll have a zero vector plus a certain thing in terms of this identity matrix. So back to the proof. Inverse of A times B. B is 0 here. So that's that first piece. Plus identity minus the product times vector Z, any vector Z with the appropriate number of components in Rm. We know that this is the form of a solution to Ax equals 0. Okay, so we're getting X of the form I minus the generalized inverse of A times A times that Z is arbitrary. Then look at I minus the product vector Z. What you're getting is multiply these out, you're getting elimination columns of the coefficient matrix, the matrix I minus general inverse times A. The thing of this, that's what these are as Z varies. So what you're getting out for all Z. So we can tie together then the dimension of the null space, which we've seen actually is the column space of this particular matrix in parentheses. The dimension of the null space then equals the dimension of the column space of this matrix, the dimension of the column space of a matrix. Why, that's the rank of I minus generalized inverse of A times A. And we saw earlier that that rank equals M minus the rank of A. It's the last part of theorem 3.5.2. So we can tie these two together by the observation that elements of the null space are elements of the column space of this matrix. So the dimensions are the same for those two spaces. And by theorem 3.5.2 part 5, this rank equals M minus the rank of A. So we can make the dimension of the null space to the number of, and that gives us, as commented, rank nullity equation. And these are the kinds of manipulation you do in sophomore linear algebra. You compute the rank, compute the nullity, do row reduction, right? You put row reduction. You might find bases as well. I don't think we've touched on a basis for the null space or basis for the column space. We certainly have the equipment to deal with it, but I don't think we pointed at problems that dealt with that specifically. But the rank nullity theorem 3.3.5, remember that one? We've used it enough. It's one that said the rank of the product of matrices is less than or equal to the minimum of the rank of the first one or the rank of the second one. All right, from that, we take a square matrix and take powers up, then we can draw the following conclusions. We could draw the conclusion that the rank of A times A is less than or equal to the rank of A times the rank of A. The minimum of those two, which, well, there ain't two, there's just the rank of A. So the rank of A squared is less than or equal to the rank of A. Similarly, we could write A cubed is A squared times A and draw a conclusion like this and string these together inductively. So we get that if we take powers of a matrix, then the dimension of the associated column space, that is the rank of those matrices, is non-increasing. So greater than or equal to, greater than or equal to, greater than or equal to, as we take higher and higher powers. Now we're doing this for a given matrix A, all right? Well, a given matrix A has a certain number of columns. A squared has the same number of columns and so forth. Only a conversation, of course, valid for square matrices. But if the rank is getting bigger and bigger and bigger, smaller and smaller and smaller, rank is greater than or equal to, greater than or equal to. So the rank decreases as we raise that matrix to powers, and the rank plus the nullity is constant. Well, if this one is getting smaller, this one must be getting bigger. The nullity must be getting bigger. That is, the dimension of the null spaces must be getting larger as we take that matrix A and raise it to powers. In fact, I can have these dimensional relationship and no particular geometric relationship among the spaces themselves. We do here if it's true that the null space of A is a subset space of A squared is a subspace of the null space of A cubed. Right? They need that way for this dimensionality to hold. But because if we say have a vector x such that a to the I times x equals 0, in other words, x is in the null space of a to the I power, then if we look at a to the I plus 1 times x, that's a times a to the I of x. But we just said a to the I times x equals a 0 vector. So of course we get the 0 vector out. So if we've got something in the null space of a to the I, then we've got something in the null space of a to the I plus 1. That's how we can draw that subset inclusion relationship on the null spaces. All right, let's see, is it? That one's all done. This is not unrelated to things we've done earlier. We're dealing with some direct sums and some orthogonal vector spaces. Must be dealing with orthogonal complements in some setting. The story here is if we have a system AX equals B consistent, any solution to that system is of the form X equals generalized inverse of A times B plus Z for some Z in the null space of A. All right. This, I suspect, you did in linear algebra. There was no generalized inverse stuff, but you did this kind of thing. If you had a consistent system, you could express came from our our textbook in terms of solution systems equations. So I can put a geometric interpretation if I don't get the standard position. I can put a geometric interpretation on the systems of equations. They're translations of vector spaces. This is a translation, and the space that's translated is ultimately written as the null space. They orthogonal space. We never had a simple space. We had a simple column space. So to talk about column spaces, we take the row space of the transpose of the matrix. And thirdly, for any matrix A, the space direct sum with the row space of A is Rm, where M is explicit. That some information to follow as well. Okay. All righty. Solutions can be expressed in this form. All right. AY equals B. That's what it means to be a solution. We know that if B is a solution, then the generalized inverse of A times B is a solution. So we can rewrite this between these two outer things. So let's subtract from the right-hand side. So move this over to the left-hand side. It goes over as a negative. We'll get a 0 on the right-hand side when we do that. And then let's factor. Factor the A out, and we'll get A times Y minus generalized inverse of A times vector B. And we'll know that equals 0 by the algebra just argued. So here's something. When we apply A to it, multiply it on the left by A, we get 0 out, 0 vector. So this something, this y minus generalized inverse of AB, that's an element of the null space because it's, when multiplied by A, it gets 0. So Z is, as we desired, an element of the null space. So we'll solve this equation for y. We get y equals generalized inverse times B plus Z. Just take that to the other side of the equation. For Z in the null space, and that's exactly what we were claiming. Vector in the null space of matrix A is perpendicular to any vector in the row space of matrix A. All right, take an element of the row space. I got this transpose stuff we'll have to deal with, but that's going to turn out to play a convenient role. Let B be an element of the null space. Let's take an inner product. We're going to get 0 out, and that's what we're trying to show. Okay, we can write inner products by transposing the first vector, multiplying it by the second. That'll give us a row times column thing. Remember, we're treating all vectors as column vectors at this stage. So the inner product can be written as such. Okay, A is an element of the column space of A transpose. The column space of A transpose, that's the row space. Right? Speak of it in terms of A transpose. So A is an element of the column space transpose. Then A is a linear combination of columns of A transpose. How could you express a linear combination? By taking that matrix and multiplying it on the right by a vector. Those components of that vector, call it S, are the coefficients of the columns of A transpose that produce A. All right, since A is in the column space, it's a linear combination of the columns of A transpose and can be written like this for some linear combination. Collect together those coefficients in a vector and call it vector S. So we can take the A and express it as a linear combination of the columns. We can write it as A transpose times S. I have no clue what S is. She'll tell me what A is. We can associate these first two things together in property transposes. Transposes, but in the reverse order, back from section 3.2. Okay. We know B was given to be in the null space of A. We haven't used that information yet. So when we take A and apply it to B, being in the null space, we'll produce the 0 vector times vector S produces out a 0 scalar. Actually, you see we got a transpose vector in S here. This is actually an inner product right here, a dot product if you like. We get the 0 scalar out. All right, and so we've got orthogonality. We took something from the row space, right, and something from the null space and showed an inner product is 0. So that means orthogonality from the null space is orthogonal to anything from the row space. Weird way to write the row space, but that's what we've got. Okay, so we've got the orthogonality. The next claim is for any matrix A, the direct sum of the null space and the row space equals R. Okay, well, this is kind of a subtle little argument. We know from the rank nullity equation, the dimension of the null space plus the dimension of the row space equals the number of columns in M. That we just said, we written slightly differently, but this is what the rank nullity equation means. Okay. Now, null space of A and the null space of A trans, both these are subsets of RM. And also, I should observe, we know they're under those conditions, we can take direct sum. Direct sum defined by, I need to choose that. So when we direct sum, we're going to get an n-dimensional subspace. When you take direct sums, we went through this section or two ago, we can talk about dimensions of a direct sum as the dimension of the null space plus the dimension of the space equals m. So the dimension of the direct sum space also equals m. When we have these perpendicular, we'll do spaces, when we have these direct sums, we can calculate dimensions by adding together dimensions of the pieces of that direct sum. So this here is an m-dimensional subspace M. Well, Rm, the only subspace that has a dimension m is Rm itself. And we can maybe use a few more details on that. But indeed, we've an m-dimensional subspace of Rm, we must have all of them. So that direct sum itself equals Rm as claimed. Let's see, I guess that was the end of that one. Oh, excellent. Okay, some follow-up on that. Let's see, we saw upstairs null spaces, if we consider powers, right, we're comparing the null space of A to the null space of A squared to the null space of A cubed and so forth. It's a pretty specific setting, arguably. So we've got this nested null spaces. We also, when we take the null space of any null matrix, direct sum of the right space of that same matrix, get Rn. Since we've got this nesting here, these spaces must be getting bigger as that exponent on matrix A increases. We've got, in a sense, the unioning together, in a sense, to give Rn. So it must be these spaces are getting smaller to preserve that direct sum. Given that exponents are increasing. So we're talking what? Row space of A, right? Row space of A, transpose space of N and space squared and space of H and so forth. So I want to mention a little bit of the flat because that's I then was something geometric. 3.5 general solution can be expressed in the form x equals this particular solution, general inverse A times B plus Z, where it was any element of, ended up being the null space. And this as, like I said, a particular solution. Think of this as a particular solution, and this is general element in space and general associated homogeneous. I don't know you did this in here algebra. You wrote general solutions plus a general solution to an associated homogeneous system of equations. Almost every one of them words will translate over to differential equations, and you'll find a general solution to a non-homogeneous differential equation by finding a particular solution and adding to it the general stated homogeneous differential equation. Linear differential equations, where all the linear algebra is valid. This particular solution is a translation. And the general solution of Ax equals T is translation space. There's a vector space and there's a translation vector. So we're writing general solutions as translations of vector spaces. This may not be a vector itself. Right? It might not have a zero vector for one thing. The null space thing, this thing may have a vector space. That's where we'll talk about prefer calling it vector space, translation of the null space. It's called or an affine space of R. The book I use in linear null space. We're in a space and translate. What you might think in your head is, okay, let's see, we were in R3, m equals 3, so we're doing something in R3. R3. So if I'll take null space and draw all them vectors in standard position in R3, that'll determine a plane that passes through the origin. You don't put them in standard position, they could be anywhere because vectors don't have position. I'm putting them in standard position. Then we'll get something that describes a plane. So a two-dimensional subspace would be a plane. And that's a perfectly good geometric interpretation with the vectors in standard position. But it's got this thing added to it when I talk not about the null space itself, but about this collection of vectors. All right. Well, then what you've done is you've taken that plane and translated it by this little vector here. So now, whereas the null space could have been represented as a plane passing through the origin in a three-dimensional coordinate system, this will be a plane that maybe doesn't pass through the origin. I want to say it passes through on it. So we get a plane now not passing through the origin. We get a plane, say, that doesn't pass through the origin in R3. There's plenty of those you can visualize. If it doesn't contain a vector, if it doesn't pass through the origin, when everything's in standard position, it ain't a vector space. But it still has this geometric interpretation of being a K-flat or an affine plane in R3. A geometric plane, if you like. But none of this plane stuff makes sense, be it subspaces or flats, unless you put the vector in standard position. And that takes care of section 5.3. I'm going to take a breather and I'll see you in the next section soon enough. It's 5.3. This is section 5.5. Old Bob's tired. I'll